Hello there. Welcome to the Sleepy Thought Channel. Tonight, we'll be drifting into the farthest reaches of outer space and exploring some of the most distant galaxies we have ever discovered. There are immense clusters of stars shaped by gravity and cosmic forces stretching back to the early universe. When we look towards them, we are looking across unimaginable distances and into a deep past where the universe was still learning what it would become. Distant galaxies carry stories of creation and transformation. They reveal how matter drew together across space, how stars first ignited, and how structure gradually emerged in the young universe. Some glow brightly with youthful energy. Others appear calm and settled, having burned through their brightest days long ago. Each one offers a clue about how the universe evolved and how our own cosmic home fits into that much larger picture. If you enjoy these gentle journeys, I invite you to subscribe, or share a thought below. It helps others find their way here, to one sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften, let your breathing slow, and allow your thoughts to loosen their grip. As your eyes begin to grow heavy, join me as we wander through the cosmos together. Let's begin. The farthest galaxies we see are also the universe's earliest chapters. When a telescope catches their light, it is catching a message that began traveling when the cosmos was young. That means distance and time are braided together. Nearby galaxies show the universe in its later karma years. Father ones show it during its restless childhood, when everything was smaller, hotter, and still taking shape. Astronomers build a kind of timeline by comparing these different distances, then looking for patterns that change with age. You can watch stars being made. You can watch shapes settle from ragged to orderly, and you can watch the first heavy elements spread outward from dying stars. It is history written in photons. The remarkable part is that the pages have not vanished. They are still arriving night after night, right on schedule. Some distant galaxies shine from a time before our sun existed. Our sun is only about 4.2 billion years old. Many galaxies we observe are so distant that their light began its journey long before the sun and earth formed. In that era, the Milky Way was still assembling, and the periodic table was missing many of the ingredients we now take for granted. Early generations of stars had to do the hard work first, forging heavier elements inside their cores, then flinging them into space through explosions. Those enriched atoms later became planets, oceans, and living cells. When you look at a galaxy from that earlier time, you are seeing a universe that has not yet learned how to make a world like ours. That is why distant galaxies feel so profound. They are a view of what had to happen before we could ever arrive. A single deep image can hold thousands of galaxies at once. A patch of sky that looks empty to your eyes can be packed with remote galaxies. When a telescope stares long enough, deep images work like patient listening. They collect faint photons one by one and stack hours of exposure until whispers become visible. In famous deep field views, the frame is often smaller than the width of your little finger, held at arm's length. Yet within that tiny slice, you can find spirals, ellipticals, and irregular shapes, all at different distances and stages of life. Some are close enough to show detail, others are barely more than a blush of light. Together they reveal a startling truth. The universe is not sprinkled with galaxies. It is saturated with them. Once you know that the night sky never feels empty again, many distant galaxies look warped because gravity bends their light. On the largest scales, gravity can act like a natural lens. A massive galaxy or cluster can curve space so strongly that light from a more distant galaxy is forced to travel along bent paths. To us, that background galaxy may appear stretched into an arc, duplicated into 2 or 4 images, or even wrapped into a near-perfect ring. These are not artistic distortions. They are maps of invisible mores. By measuring the exact shape of the warping, astronomers can weigh the lensing object and trace where its matter sits, even when most of that matter emits no light at all. Lensing can also magnify the background target, making an otherwise unreachable galaxy bright enough to study in detail. Gravity becomes both a sculptor and a spotlight, helping us see farther than our instruments could alone. The most ancient galaxies appear red because space stretches their light. As the universe expands, it stretches the waves of traveling light, pulling them toward longer red or wavelengths. So a galaxy that once shone strongly in ultraviolet can arrive at our telescopes looking red or even invisible to eyes and cameras tuned for visible light. That is why infrared observatories matter so much. They are built to catch stretched starlight that would otherwise slip past us. Red color can also hint at age. Older stellar populations tend to be cooler and redder than hot newborn stars. Astronomers tease these effects apart by taking measurement through multiple filters, then comparing the pattern to models of how stars shine. Over time, that careful work turns a simple color shift into a distance estimate and into a clue about when the galaxy stars first ignited. A reddish glow can be the signature of extreme antiquity. Colliding galaxies are common in the early universe, not rare in the young universe. Galaxies lived closer together, and their paths crossed more often. Gravity pulled them into slow-motion encounters that lasted millions of years. First came the tidal tugging, stretching out long tails of stars and gas. Then came the mixing as orbits were scrambled and clouds collided. These events did not always destroy galaxies. They often transformed them. A calm disk could be stirred into a thickened shape. Two smaller systems could merge into one larger one. Fresh gas could be driven inward, setting off intense bouts of star formation in regions that were previously quiet. When astronomers look far back, they find a zoo of distorted shapes that make perfect sense in a universe built by assembly collisions or part of the growth perm. The galaxies we see today carry the fingerprints of those ancient meetings, even when their outlines look serene. A galaxy's color can reveal whether it is building stars or resting. Color is not just decoration in space. It is a clue about what kinds of stars are dominating the light. When a galaxy is actively forming new stars, it tends to glow bluer because hot young stars pour out energetic light. When star formation slows, the bright blue stars fade quickly, and the longer-lived redder stars become the main voices in the chorus. Astronomers use carefully chosen filters to measure these color differences and compare them to models of stellar populations. It becomes a kind of mood reading, but grounded in physics. Some galaxies look like they are still in the middle of a bustling building phase. Others look settled, like a town after the festival has ended. Even dust leaves a signature by reddening light in a different way than aging does. With only a few bands of color, a galaxy can tell you whether it is busy paused or hiding its activity behind a veil. The earliest galaxies grew fast through non-stop mergers and fresh gas. In the early universe, growth was more like rush hour than quiet suburbia. Small galaxies were everywhere, and gravity kept pulling them together. When two met, their stars did not usually collide because space between stars is vast. Instead, the galaxies intermingled, and their gas clouds were jolted and compressed. At the same time, new gas flowed in from the surrounding cosmic environment, feeding more star formation and adding mass. This constant supply helped early galaxies bulk up quickly, even when individual pieces were modest. Over time, repeated encounters could turn a loose collection of clumps into a larger, more organized system. Astronomers look for signs of this rapid assembly in the shapes of distant galaxies and in how their gas and stars are distributed. It is a story of construction under pressure, where the materials kept arriving and the blueprint kept changing. Distant galaxies can be hidden in plain sight behind cosmic dust. Dust is made of tiny grains closer to smoke than sand, and it is incredibly good at blocking visible light. In a distant galaxy, dust can wrap around star-forming regions and hide them almost completely. To a visible light telescope, the galaxy may look faint and unimpressive, yet in longer wavelengths, the story flips. Dust absorbs energetic starlight, warms up, and then re-emits that energy as infrared and millimeter radiation. Instruments that can detect those wavelengths reveal galaxies that are forming stars at astonishing rates, even while they appear dim in ordinary images. This is one reason our view of the universe kept changing as new kinds of telescopes arrived. Dust did not merely decorate galaxies, it concealed some of the most active ones. By seeing through it, we uncover a more complete census of cosmic star building, and we learn how quickly galaxies can grow behind a curtain. Star formation once peaked across the cosmos like a universal fireworks season. There was an era when the universe was especially busy making stars. Astronomers sometimes call it cosmic noon. Because it was a high point in activity, galaxies were rich with cold gas, and that gas could collapse into new stars more readily than it does today. Many galaxies were also interacting and merging, which helped compress gas and trigger bursts of star birth. Over time, that frenzy eased. Gas supplies were used up, heated, or pushed out by energetic processes, and the average rate of star formation declined. The universe did not stop making stars. It simply became less intense, more measured, and more selective. Knowing when that peak happened helps astronomers understand why galaxies look the way they do now. It explains why many massive galaxies are filled with older stars, and why the night sky contains relic light from a brighter past. The same telescope can show both baby galaxies and mature giants. A single telescope can act like a storyteller with many chapters open at once. In one field of view, a nearby galaxy might show crisp spiral arms and stable star-forming neighborhoods. In the same image, a much more distant galaxy may appear smaller and rougher because we are seeing it at a younger stage in cosmic time. The instrument has not changed. The light has. Different distances mean different ages, and the camera simply records what arrives. This lets astronomers compare young and old systems without switching to a new sample or a new method. The same calibration, the same optics, and the same observing strategy can be applied across the scene. It is like holding a family portrait that includes infants, adults, and elders, all captured in one frame that makes patterns easier to trust and surprises harder to ignore. One observation becomes a cross-section of cosmic evolution. Some distant galaxies are seen as faint smudges, yet contain billions of stars. When you look at a deep sky image, some galaxies barely rise above the background. They can look like a soft fingerprint on black velvet. Yet that faintness is not smallness. It is distance and the brutal honesty of physics. Light spreads as it travels, and the galaxy's glow is diluted across an enormous sphere of space. Add in dust, aging stars, and the limits of our detectors, and even a giant system can seem shy. Astronomers pull meaning from that shy light by measuring its shape, its color, and how its brightness changes across the image. From those clues, they estimate how many stars must be there to produce what we see. It is a strange kind of revelation. A tiny blur can represent a city of suns. The universe hides its grandest crowds inside its quietest specks. Some galaxies are so bright because black holes are feeding inside. In the heart of many galaxies sits a supermassive black hole. When gas falls toward it, the gas does not vanish quietly. It spirals into a hot, crowded disk, and friction heats that disk until it shines with staggering power. The light can outshine the combined starlight of the entire host galaxy, turning the core into a beacon, visible across billions of light years. This is how quasars announce themselves. They are not powered by nuclear fusion like stars. They are powered by gravity, converting and filling matter into energy with remarkable efficiency. In some cases, the brilliance can change over weeks or months, hinting that the glowing region is compact. That flicker is a clue about the scale of the engine. When you spot one of these bright cores, you are witnessing a galaxy with an active heart feeding and blazing in the dark. Some galaxies are quenched, meaning starbirth stopped long ago. But quenched galaxy is not dead. It still contains stars, and those stars keep shining for billions of years. What has changed is the arrival of new stars. The supply line has been cut, or the conditions needed for star formation have been disrupted. Sometimes the galaxy has used up much of its cold gas. Sometimes that gas is being heated, so it cannot collapse into new stellar nurseries. Sometimes energetic events in the core or the surrounding environment prevent fresh fuel from settling. The result is a galaxy dominated by older star white with fewer bright young stars to refresh its glow. Astronomers identify these systems by their colors, their spectra, and by the lack of telltale signs of hot newborn stars. Crunching matters because it marks a turning point in a galaxy's life. It is the moment when a galaxy stops adding new voices and begins to age with what it already has. Distant spiral shapes can appear surprisingly early despite cosmic chaos. Spiral galaxies feel like a late, polished outcome, like something that should require time and stability. That is why it can be startling to find spiral patterns far away when the universe was younger and more crowded. Spirals are not painted on, they are patterns that emerge from motion. A star's and gas orbit in a disk and gravitational waves ripple through it. For a disk to form a galaxy must settle its gas into a relatively flat rotating structure rather than staying as a jumble. Seeing spirals early suggests that some galaxies found their balance faster than expected. It also raises questions about what helped them stay stable in a rough neighborhood filled with interactions. Astronomers study these early spirals to learn how disks survive, how quickly order can emerge, and how the familiar shape of our own galaxy could have started. Bedtime taking form long before the solar system existed. Many early galaxies look clumpy because their gas collapses and giant knots. Instead of neat spiral arms, many distant galaxies look like scattered islands of brightness. Those bright patches are often enormous star-forming regions, far larger than typical star-forming complexes in nearby galaxies. Early galaxies carried large reservoirs of gas, and that gas could become unstable, breaking into massive clumps under its own gravity. Inside each clump, stars can form in intense bursts, lighting it up like a beacon. Over time, these clumps can merge, and migrate inward, helping reshape the galaxy's structure. Astronomers track this company as a clue to how galaxies built their central regions, and how they turned chaos to gas into organized systems. The clumps are not random noise. They are the visible marks of a young galaxy, doing heavy lifting, converting raw material into starlight in oversized workshops. When you see a clumpy galaxy, you are catching growth in action, not a finished design. Some galaxies are so compact, they fit enormous mass into tiny space. Some distant galaxies look small, yet their gravity tells a different story. They compact the mass of a large galaxy into a region on the affection of the size you might expect. That means stars' crowded orbits are fast, and the internal motions can be extreme. Astronomers infer this compactness by measuring how light is concentrated and by studying spectral lines that reveal how quickly stars or gas are moving. These compact systems are fascinating because they may be early versions of today's giant galaxies, caught in a brief, intense phase before they puffed up through later growth. How do you build something so dense without tearing it apart? Did it form from a rapid collapse of gas or from early mergers that funneled material inward? Compact galaxies are like cosmic pressure cookers. They show that the universe can assemble huge structures quickly, and that size alone is not a reliable guide to importance. Giant elliptical galaxies often formed through repeated collisions, not calm growth. Elliptical galaxies can look smooth and serene, like they have always been that way. Their histories are often the opposite. Repeated mergers can scramble stellar orbits, erasing the tidy rotation of a disk and leaving stars moving in many directions. Over time, that kind of mixing produces a rounded, featureless glow. In some ellipticals, you can still find faint shells, ripples, or subtle twists in the light. These are leftovers from past encounters, like wrinkles that never fully iron out. Ellipticals also tend to host older stellar populations, which hints that much of their star formation happened earlier. Then the system settled into a long, slow aging process. Astronomers study ellipticals because they are in states the products of many previous chapters. They remind us that a calm appearance does not mean a calm past, sometimes the smoothest. Galaxies are the ones that survived the most upheaval. Dwarf galaxies can be small, but they are crucial for cosmic history. Dwarf galaxies are the lightweights of the galaxy world, but they carry heavyweight clues. Because they have fewer stars and weaker gravity, they respond dramatically to processes that larger galaxies can shrug off. Their gas can be blown out more easily, their star formation can start and stop and fit, and their chemical makeup can stay simpler for longer. That makes them valuable time capsules. Some dwarfs preserve evidence of early star formation and early enrichment because their histories are less blended than the histories of giant galaxies that have merged many times. Dwarfs are also thought to be common building blocks, the small systems that larger ones grow from by accretion. By counting dwarfs, measuring their motions, and studying their stars, astronomers test ideas about how galaxies assemble and how invisible mass shapes structure. If you want to understand the universe's growth strategy, you cannot ignore the small players. Often the smallest galaxies keep the cleanest records. Some dwarf galaxies are being torn into star streams by larger neighbors. Gravity is not always a gentle shepherd. When the dwarf galaxy orbits a larger one, the pool can stretch it, and repeated close passes can peel stars away. Those stars do not vanish. They form long, thin rivers that wrap around the host galaxy, sometimes for huge arcs across the sky. These streams are more than beautiful. They are evidence of ongoing assembly, a reminder that galaxies are still growing by, capturing smaller companions. Streams also act like test particles. Their shapes and paths respond to the unseen mass around the host, so mapping them helps reveal the structure of the host's gravitational field. Astronomers hunt for these streams in deep imaging, then confirm them with measurements of stellar motions and chemistry. It is a slow dismantling, but it is also a kind of memory. Even after the dwarf is mostly dispersed, its stars can keep tracing its former orbit, writing the story of the encounter in a luminous loop. The Milky Way is only one island in a vast sea of galaxies. It is easy to feel like our galaxy is the main stage, because it is the one we live inside. Modern surveys have shown a bigger truth. Galaxies fill space in every direction, and even a seemingly blank patch of sky can hold countless remote systems. Each galaxy is a self-contained ecosystem with its own history of star birth, chemical change, and gravitational drama. Some are tiny and dim, others are enormous and crowded with old stars. When we call the Milky Way an island, we are also admitting something humbling. Islands can have neighbors, and seas can be endless. The night sky becomes a map of other places, not just other lights. When you picture that scale, you also pictured time, because much of that light began traveling before humans existed. Looking outward is a way of meeting the larger universe. Galaxy groups are common, and loneliness is rarer than company. Many galaxies do not live in splendid isolation. They gather in groups held together by shared gravity, and they influence one another for billions of years. In a group, galaxies can pass close enough to tug on each other, stirring up gas and bending outer stars into faint streams. Even when they do not collide, their mutual pull can reshape their orbits and change how fresh gas is delivered. Groups are also where galaxies begin to learn their place in the cosmic neighborhood. Some become dominant, some become satellites, some get gradually stripped of material during repeated encounters. This matters for us because the Milky Way is part of a group too. Studying distant groups lets astronomers compare many different galactic families, then ask what conditions make galaxies thrive, fade, or transform. It is a reminder that galaxies have social lives, and their stories are often written in relationships. Galaxy clusters can contain thousands of members, bound by gravity. A cluster is a city on a cosmic scale. It can hold thousands of galaxies, along with vast reservoirs of hot gas and enormous amounts of unseen mass. The space between the galaxies is not empty. It can blow in X-rays because the gas is heated to extreme temperatures by the cluster's deep gravitational well. Inside this environment, galaxies move at tremendous speeds, and close passes can be frequent that high-speed traffic can alter. Galaxy shapes strip away gas and leave some members with little fuel to form new stars. Clusters are also useful tools. Their combined mass can bend light from objects behind them, and their size makes them visible across great distances. When astronomers map clusters, they learn how matter gathers over time. They also learn how the universe builds its largest bound structures. A cluster is not just a collection, it is a laboratory that spans millions of light years. Between clusters lie enormous voids where galaxies are scarce. If clusters are crowded cities, cosmic voids are wide, quiet countryside. These regions can stretch for tens of millions of light years, with far fewer galaxies than average. Voids are not completely empty, but the matter inside them is thinly spread. That scarcity is part of the story of how the universe evolved. Tiny differences in density after the Big Bang grew over time. Dense regions pulled in more matter and became clusters. Less dense regions lost the tug of war and emptied out. When astronomers map voids, they are not only counting what is missing, they are measuring how structure grew and how gravity and cosmic expansion shape the distribution of matter. Voids can also help test cosmology because their sizes and shapes depend on how the universe expands and how matter clumps. A surprising thing is that emptiness has a pattern. Even the quietest places in the cosmos carry information. Galaxies trace a cosmic web stretched across unimaginable distances. On the grandest scales, galaxies are not scattered randomly. They outline filaments and sheets that connect clusters, and those connections form a vast web across the observable universe. Imagine bright beads on invisible threads. The threads exist because matter flowed along preferred paths under gravity, guided by the initial ripples in the early universe. Gas followed these pathways too, and gas is the ingredient that makes stars. That means the web is not just a map of where galaxies are. It is also a map of where galaxies can be fed. Astronomers reveal the web by surveying huge volumes of space, then turning millions of galaxy positions into a three-dimensional structure. The result is both beautiful and useful. It helps explain why clusters sit at filament intersections, why voids open between them, and why the universe looks like a network rather than a mist. Our galaxy sits in this web too, carried on a strand of structured dark matter halos, guide where galaxies form like invisible scaffolding. A galaxy's visible stars are only part of the story. Most galaxies seem to sit inside a much larger halo of unseen mass. This dark matter does not shine, and it does not absorb light, but it exerts gravity. That gravity helps pull ordinary gas into a growing clump, and it can hold that gas long enough for stars to form. Without this hidden framework, many galaxies would struggle to assemble as efficiently as they did. Halos also influence the shapes of galaxies and the motion of their stars. In simulations, galaxies often appear where dark matter first gathers, and then the luminous material follows the gravitational blueprint. Astronomers cannot take a direct photograph of a halo, but they can detect its effects through motions and lensing. The idea is simple, and the implications are enormous. Much of the architecture of the universe is built from something we cannot see. We learn its presence from how everything else behaves. We infer dark matter because galaxies spin too fast for their visible mass. If you could weigh only the stars and gas, you can see many galaxies would not hold together. Their outer regions orbit so quickly that the visible material cannot provide enough gravity to keep those stars bound. Something extra must be there. This insight came from careful measurements of how orbital speed changes with distance from a galaxy center. The surprising result was not a neat decline in speed, it was a stubborn persistence. The outskirts kept moving fast. That behavior suggests a large extended reservoir of mass surrounding the galaxy. This conclusion is not based on one galaxy or one method. It appears across many systems and many observing techniques. Dark matter becomes the simplest explanation that fits the pattern. The consequence is wonderfully strange. The part of a galaxy we can see is like the lit windows of a city at night. The mass that shapes the city's gravity is mostly in the darkness around it. Galaxy rotation gave us one of astronomy's biggest clues that the universe contains more than meets the eye. Some distant galaxies reveal dark matter through lensing arcs and rings. When a massive object sits between us and a more distant galaxy, the foreground gravity can bend. background light into dramatic shapes. Long arcs can appear around clusters, and nearly perfect rings can form when the alignment is just right. These shapes are not random. Their curvature depends on how mercy is distributed in the lens that includes both the ordinary matter we can see and the much larger contribution from dark matter. By modeling the arcs and rings, astronomers can reconstruct a mass map, and they often find that the visible galaxies account for only a small fraction of what is Changru required. Lensing is powerful because it does not care whether the mass is glowing. Gravity bends light the same way, either way. In a sense, lensing lets distant galaxies act as backlights. They illuminate the invisible structure in front of them, and they turn geometry into a weighing scale. Each arc is a signature of hidden mass written in starlight. Lensing can magnify a distant galaxy, turning a whisper into a signal. Sometimes a faraway galaxy is too faint to study in detail. Its light is real, but it arrives in too small a trickle. Gravitational lensing can change that. When a lensing mass focuses the light, the background galaxy can be boosted in brightness and stretched across the detector. That stretching can reveal structure that would otherwise be blurred into a dot. It can even make spectroscopy possible, so astronomers can measure chemical fingerprints and gas motions in a galaxy that would be unreachable without help. This is not a trick of image processing. It is nature providing a larger aperture through curved space. The price is complexity, because the image is distorted and must be modeled carefully. The reward is access. Lensing has opened windows onto the early universe by letting us study galaxies that are intrinsically small, very young, or heavily obscured. It is one of the rare cases where the universe itself lends us an instrument and we learn to use it. Sometimes lensing creates multiple images of the same faraway galaxy. A strong lens can split one background galaxy into 2, 4, or even more separate images arranged around the foreground mass. Each image takes a different path through curved space, and those paths can have different lengths. That means the light can arrive at different times. If the background source changes in brightness, you may see the change appear in one image first and then later in another. This can turn the sky into a natural timing experiment. Astronomers use these delays to test their lens models and to infer properties of cosmic expansion. On rare occasions, a transient event can be seen multiple times with a later appearances, predicted in advance because the paths are known. That is one of the most mind-bending payoffs of lensing. You are not only seeing the same object more than once, you are seeing it at different arrival times, as if the universe is giving you several versions of the same message delivered on different routes. A quasar can outshine its entire host galaxy for a time that sounds impossible until you remember what it's doing. The brilliant source is not a swarm of stars. It is matter falling inward, heating up as gravity squeezes it tighter and tighter. In that crowded region, gas can reach temperatures that make it radiate fiercely across the spectrum. The glow can be so intense that the surrounding galaxy becomes hard to see, like a city skyline lost behind a stadium floodlight. Quasars were once mysterious stars, like points that did not behave like stars at all. Their great distances turned them into cosmic lighthouses visible when most normal galaxies at the same era would be too faint. They also teach a sobering lesson about scale. A region no larger than our solar system can dominate the light of a galaxy that spans hundreds of thousands of light years. Quasars let us study the early universe because they are visible so far. When a quasar's light crosses the cosmos, it does not travel through emptiness. It passes through thin gas between galaxies, and that gas leaves tiny bite marks in the quasar spectrum. Those bite marks become a record of what the universe was like along that line of sight, including how much neutral hydrogen remained and how enriched the gas was by earlier generations of stars. In this way, a quasar becomes more than an object. It becomes a backlight for a long, invisible landscape. Astronomers can use many quasars spread across the sky to build a patchwork view of intergalactic matter at different distances and times. That helps reveal when the universe became transparent to ultraviolet light and how early structures grew. It is a clever trick. Instead of trying to see faint gas directly, we let a distant beacon carry the evidence to us. Some galaxies host active cores that flicker as their black holes feed. An active galactic nucleus can change its brightness on human timescales, and that is a gift to a strong me. Rapid changes imply a compact source, because a large region cannot brighten all at once. Astronomers watch these fluctuations across different wavelengths and measure how long it takes one band of light to echo another. That delay is not just a curiosity, it is a ruler. It reveals the spacing between the glowing regions near the black hole, including the hot inner disk and the surrounding gas clouds that light up in response. This method is called reverberation mapping, and it can estimate the black hole's mass without resolving the region as an image. The story is dynamic rather than static. Feeding is not a steady sip. It is lumpy, variable, and sometimes dramatic when the core flickers. It is the universe showing you the engine is alive and adjusting in real time. Jets from black holes can stretch farther than the galaxy itself. Some active galaxies launch narrow beams of particles that race outward at near light speed. These jets can punch through the host galaxy and keep going, carving their way into intergalactic space for distances that dwarf the galaxy's own diameter. Along the way, the jets glow by synchrotron radiation, which is produced when fast-charged particles spiral around magnetic fields. At the far ends, the jets can inflate huge radio lobes like cosmic balloons, and the impact points can form bright hotspots where the flow slams into fins surrounding gas. Even if the galaxy's stars look calm, the jets reveal a violent focused process at the center. They also make black holes visible in a different way. A black hole itself is dark. A jet is a signature written across space, showing where energy is being transported far beyond the region where it was released. In the best cases, you can trace the whole path from coal to lobe like a glowing map. Those jets can heat gas and slow star formation across a whole galaxy. A galaxy may have plenty of gas and still fail to make many new stars because the gas is kept too warm and too stirred up to collapse. Jets are one way that can happen. When a jet plows into surrounding material, it can drive shocks, inflate bubbles, and create turbulence. That spreads energy through the galaxy's atmosphere. In galaxy clusters, these bubbles can appear as cavities and hot, X-ray gas clear signs that something powerful has pushed the material aside. This heating can prevent the gas from cooling back down into the dense clouds needed for star birth. It is a form of cosmic regulation, and it helps explain why some massive galaxies are full of old stars rather than continuing to grow brighter with new ones. The effect can be subtle in photographs of starlight, but it becomes clear when you look at the gas. The galaxy's future can be decided by an invisible thermostat controlled near its center. Some deluxes hide their black holes behind thick veils of dust. Not every active black hole amounts as itself with a bright, unobstructed glare. In many galaxies, dense dust and gas block the central region from view in visible light. From the outside, the galaxy can look ordinary, even calm, while intense activity is happening at its core. Astronomers reveal these hidden engines by using wavelengths that dust cannot easily stop and by looking for telltale signs of heated material and energetic particles. X-rays can pierce through many layers that would black out optical telescopes. Infrared observations can catch dust that has been warmed by the buried source, re-emitting energy that was absorbed. This is more than a technical detail. It changes the census of active galaxies in the universe. If you only look with your eyes, you miss a large fraction of the story. Hidden black holes matter because they show that growth can happen behind a curtain and that the universe does not always put its most dramatic processes on display. Infrared telescopes reveal dust warmed by stars by cosmic EMBA glow. Dust grains are tiny, but they are powerful storytellers. When young stars blaze inside dusty regions, much of their visible and ultraviolet light gets absorbed. The dust heats up and releases that energy as infrared radiation. Infrared telescopes can therefore uncover star formation that would otherwise be underestimated or missed entirely. This is especially important in distant galaxies, where intense star formation often happens in dusty environments. By measuring infrared brightness at different wavelengths, astronomers can estimate how much dust is present and how warm it is, which hints at how intense the hidden star formation may be. Infrared data also helps separate two kinds of power sources: widespread star formation and a compact active nucleus, because they leave different spectral signatures. In a sense, infrared astronomy listens for warmth rather than light. It lets you find galaxies that are building stars behind thick curtains, and it gives you a fuller, more honest picture of how busy the universe has been. Radio telescopes can map cold gas, the raw fuel for new stars. Stars formed from cold gas, and radio observations are one of the best ways to find it. Neutral hydrogen can emit a characteristic radio line, and molecular gas can be traced through molecules, like carbon monoxide, which shines in millimeter wavelengths. These signals reveal not just how much fuel a galaxy has, but where it sits and how it moves. You can see gas rotating in a disk. You can see streams flowing inward. You can see disturbed patterns that hint at recent interactions. This matters for distant galaxies because starlight alone can hide the supply chain. A galaxy might look faint in the optical, yet contain a huge reservoir of cold gas waiting to form stars. Radio and millimeter maps turn that invisible reservoir into a picture, and they let astronomers connect cause to effect. Star formation is not magic, it is logistics. Cold gas is the inventory, and radio telescopes are how we take stock across the universe. Ultraviolet light highlights hot young stars, but dust can erase the view. If you want to find where new stars are forming, ultraviolet light is a direct clue. Massive young stars burn hot and shine strongly in ultraviolet wavelengths, and they do so for only a short time before they explode or fade. That makes ultraviolet a kind of freshness indicator. When you see ultraviolet glow, you're seeing recent star formation, not ancient history yet. Ultraviolet is also fragile information. Dust absorbs it efficiently, which means a galaxy can be forming many stars and still look ultraviolet faint. Astronomers deal with this by combining ultraviolet with infrared. The ultraviolet shows what escapes, and the infrared shows what was absorbed and re-emitted. Together, they bracket the truth. Ultraviolet observations have also enabled clever ways to find very distant galaxies, because intergalactic hydrogen can block ultraviolet light below certain wavelengths, creating a distinctive drop in brightness. That drop becomes a distance clue, letting astronomers sift the far universe from the near. Astronomers combine many wavelengths to rebuild a galaxy's full story. A galaxy is not one thing. It is stars, gas dust, magnetic fields, and sometimes an active black hole, all layered together. No single wavelength can capture all of that at once. Visible light shows starlight, and structure infrared reveals hidden star formation and warm dust. Radio and millimeter trace cold gas and energetic particles. X-rays highlight hot gas and extreme environments. When astronomers stitch these views together, they can build a coherent narrative, including where the fuel is, where stars are forming, how energy is moving, and whether a central engine is dominating the galaxy's life. This is why the same galaxy can look peaceful in one band and wild in another. Multi-wavelength work also prevents easy mistakes. A bright galaxy might be powered by star formation, or it might be powered by a compact nucleus, and the difference matters for cosmic history. In the end, a galaxy story is a layered song, and each wavelength carries a different part of the melody. Redshift is a cosmic speedometer, showing how fast galaxies recede. Light carries a subtle clue about motion. When a distant galaxy is moving away, as space expands, its light arrives stretched toward redder wavelengths. Astronomers measure that shift by spreading the light into a spectrum and finding familiar fingerprints from atoms like hydrogen. Those fingerprints land slightly displaced, and the size of that displacement tells how strongly expansion has pulled the light during its journey. It is like hearing a siren drop in pitch as it passes, except the effect is written into color itself. With redshift, a galaxy becomes more than a faint patch. It becomes a data point in a grand pattern of expansion. Measure many galaxies, and you can watch the universe swell over time. It is one of the rare cases where distance, motion, and history are encoded in a single measurable change of light. Great. A redshift usually means greater distance in earlier cosmic time because light takes time to travel. A very distant galaxy is also a very old view. Redshift helps sort these views into a sequence. Higher redshift typically means the light has been stretched more, which usually means it has traveled longer through expanding space that lets astronomers arrange galaxies by era. Then, compare what they looked like at different stages of the universe. You can place full irregular systems alongside later more settled ones and ask what changed. You can test when star formation was most active and when galaxies began to look more familiar. There are caveats because local motions add small wrinkles. Even so, the overall trend is a powerful guide. It turns the sky into a layered archive, where looking farther does not only mean looking deeper into space, it means looking deeper into time toward the early building years of galaxies and the universe itself. The expansion of space can carry galaxies away faster than light without breaking physics. This sounds like a rule being broken, yet it is a different kind of motion. Special relativity limits how fast objects move through space. Cosmic expansion is space itself stretching, and that stretching can increase the distance between faraway galaxies at an effective rate greater than the speed of light. No galaxy is out racing a light beam in its local neighborhood. Instead, the fabric between neighborhoods is growing. This is why there are regions we cannot ever reach even with an ideal rocket. It is also why some galaxies are visible, only because their light began traveling when they were closer in a smaller universe. Over time, expansion can turn reachable into unreachable, invisible into forever beyond. The idea is both unsettling and beautiful. It says the universe has a dynamic horizon, and its limits are shaped by growth, not walls. We never see a galaxy now, only how it looked when its light left. Every telescope is a time machine with a simple engine. Photons take time to cross space, so the image you receive is a delayed message. For a nearby galaxy, the delay is still immense on a human scale. For a very distant one, the delay reaches into the deep past. That means the universe presents itself as a mixture of arrays at once. In one sky survey, you can catch a relatively mature galaxy nearby and a far younger one in the same frame. This is not a trick of interpretation. It is the literal consequence of finite light speed. Astronomers embrace it by building timelines from distance. They compare population to cross redshift. They look for trends and they search for turning points where galaxy growth changed pace. It is a humbling perspective. The present is not on display. What we see is a vast collection of past moments arriving together in a single night. Some galaxies may no longer exist, even though their light still arrives. A photon does not update itself with current events once it leaves a galaxy. It carries the story of that moment and nothing afterward. Over billions of years, that galaxy could collide, transform, or be disrupted, and the traveling light would not know. So it is possible to observe a galaxy as it once was, even if its later fate has already unfolded. This creates a strange kind of cosmic lag. A sky can contain scenes that are in a real sense historical records of objects that have changed beyond recognition since the light departed. Astronomers think in these terms. When they reconstruct evolution, they do not assume a distant galaxy is still in the same state today. They treat it as an ancient snapshot, then place it into a larger sequence of snapshots from many distances. It is like receiving postcards that were mailed across ages, each one stamped with the time it began its journey. Starlight can travel billions of years, yet cross your telescope in moments. The journey is almost unimaginable. A single photon may leave a distant galaxy and spend most of the universe's history in flight, passing through expanding space and slipping between galaxies. Then it reaches Earth and meets your telescope, and that final encounter is over instantly. Billions of years of traveler gathered into a single click of a detector. This contrast is part of what makes astronomy feel magical while staying strictly physical. A deep observation is really a patient act of collecting these rare arrivals. One photon is a whisper. Many photons become a spectrum, a shape, a story. Each one is also evidence that space, though vast, is not completely opaque. The universe has stayed transparent enough for messages to cross cosmic distances. When you look at a faint distant galaxy, you are participating in an exchange that began long before humans existed and ends in a small, quiet moment. The IPSA galaxy spectrum can reveal its elements like a barcode of atoms. When you split starlight into its rainbow, you find dark gaps and bright features at specific wavelength. These are produced because atom and molecules absorb or emit light in precise ways. Hydrogen has its signatures, oxygen has its own, so do carbon, nitrogen, and many others. By measuring the pattern, astronomers can infer what a galaxy is made of, even when it is far too distant to resolve individual stars. The spectrum also carries more than composition. It can show temperature, density, and motion, because lines broaden and shift as gas moves and conditions change. This makes spectroscopy one of the most powerful tools in studying distant galaxies. It turns faint light into a chemical report, and it turns a dim smudge into a place with physical properties you can describe. The wonder is practical. You can learn what exists in a galaxy by analyzing the lights that reaches you without ever going there. Early galaxies had fewer heavy elements because stars had less time to forge them. In the early universe, most matter was hydrogen and helium, with only trace amounts of heavier elements. The richer ingredients needed for rocky planets and complex chemistry are built inside stars and then dispersed. That process takes time. A star must live, fuse lighter atoms into heavier ones, and then return material to space through winds or explosions. Early galaxies had not hosted as many stellar generations, so their gas was less enriched. Astronomers can see this in spectra, where certain metal lines are weaker, and in the ways gas cools and forms stars. Metal-poor gas behaves differently. It can change how easily clouds fragment, which can influence the kinds of stars that form. This is why early galaxies are not just younger versions of modern ones. Their materials were different. They were operating with a simpler chemical toolkit, and that difference shaped how quickly they could build, structure dust, and future star systems. The first generations of stars changed galaxies by enriching their gas. The earliest stars were pioneers in a chemically simple universe. As they aged, they manufactured heavier elements in their cores, and they seeded their surroundings when they shed layers or exploded. That enrichment transformed what galaxies could do next. Heavier elements help gas cool more efficiently, and cooler gas can collapse into denser clouds. Those clouds can then form new stars more readily, and they can form dust grains that further reshape. Organics is light and chemistry enrichment also created the raw materials for future planets and for the molecules that can make complex structures. Astronomers look for this transition by studying distant galaxies across time, searching for when metal content begins to rise and how rapidly it spreads. The change is not only about composition, it is about capability. With each stellar generation, a galaxy becomes more chemically diverse and more structurally complex. The first stars were not merely bright, they were architects rewriting their galaxies from the inside out. Supernova can blow gas outward, regulating how quickly a small galaxy grows. In a small galaxy, gravity has a lighter grip that makes it vulnerable to powerful events. When massive stars end their lives as supernova, they release immense energy into surrounding gas. The blast can heat it, stir it, and in some cases, push it out of the galaxy altogether. If enough gas is expelled, star formation slows because the fuel supply is reduced. If the gas is only heated, it may take time to cool and settle back into dense clouds. Either way, growth becomes stop and start rather than smooth. This feedback helps explain why some dwarf galaxies form stars in bursts separated by quiet periods. It also influences chemical evolution because gas flowing out can carry newly made elements away before they mix thoroughly. Supernova feedback is a kind of galactic self-control. It prevents small galaxies from turning all their gas into stars too quickly, and it helps set the pace of their long, uneven lives. Some galaxies undergo starbursts, forming stars at furious rates. For a short stretch of cosmic time, a galaxy can behave like it is pressed an accelerator. Gas that might have formed stars slowly is driven into dense pockets, and those pockets light up with new star clusters. In nearby examples, starburst regions can be crowded with massive short-lived stars whose intense radiation reshapes their surroundings. In distant galaxies, the effect can be so strong that the system glows brilliantly in infrared. Because dust absorbs starlight and re-radiates it as heat, starbursts do not last long on a galactic clock. They burn through fuel, and they stir the gas with winds and explosions. That is what makes them so valuable. Catching one is like catching a thunderstorm. You learn what galaxies can do at their most extreme, and you learn what stops them from doing it forever. Starbursts often follow collisions when gas is compressed like squeezed clouds. When two galaxies pass close, gravity does more than tuck their stars. It talks their gas, stealing some of its angular momentum and pushing it inward. As gas streams converge, they collide and shock, and the pressure rises fast. That is the squeeze that can turn large, puffy reservoirs into dense, star-forming clouds. In some mergers, bright knots appear where tidal forces pile gas into overlap regions, and those knots can become nurseries for superstar clusters. Collisions also scramble orbits, so gas that once moved in orderly paths begins crossing itself. That chaos is productive. It increases the chances of cloud collisions, and it can trigger waves of star formation that grace through the system. Eventually, the same violence that started the burst can help end it because feedback heats and disperses the remaining gas. A merger is both a spark and a stopwatch. Distant galaxies can host vast nebulae glowing from energetic young stars. Around some galaxies, especially in the early universe, the glow can extend far beyond the main starlight. This light often comes from gas that is being lit up by young massive stars or by the energetic processes near the galaxy's center. The nebula can act like a lantern shade, revealing where gas is sitting and how it is moving. Astronomers look for specific emission lines that signal excited hydrogen, and they map how those lines shift across the nebula to infer motion. Sometimes the glow outlines outflows that are streaming away from the galaxy. Sometimes it traces inflowing material that is feeding future star formation. These extended nebulae make galaxies feel less like isolated islands and more like creatures with atmospheres. The stars are the bright core, but the surrounding gas is the living interface where growth and change are negotiated. Some galaxies leak ultraviolet light, helping rhynize the early universe. In the earliest epochs, the space between galaxies contained lots of neutral hydrogen, which is very effective at absorbing ultraviolet light. For the universe to become transparent enough, energetic photons had to escape from galaxies and reach the antigalactic gas. Not every galaxy can do this. Ultraviolet photons are easily trapped by dust and by dense clouds of hydrogen inside the galaxy itself. Escape becomes easier when stellar winds and supernova carve channels through the gas, or when star formation happens near the edges of the galaxy where there is less material in the way. Astronomers hunt for these leaky galaxies by looking for spectral signatures that suggest ultraviolet photons are getting out. When they find candidates, they are finding more than curiosities. They are finding potential agents of a major cosmic transition. When the fog of neutral hydrogen began to clear across the universe, reionization ended the cosmic dark ages, making space more transparent to light. After the Big Bang cooled enough for electrons and protons to join, much of the universe became neutral, and that neutral gas absorbed energetic light very efficiently. In that period, the first luminous objects had not yet fully transformed their surroundings. Over time, early stars and galaxies produced ultraviolet radiation that broke hydrogen back into ions. This change spread outward in growing grain-vat bubbles. Eventually, those bubbles overlapped until most intergalactic hydrogen became ionized again. Once that happened, ultraviolet light could travel more freely, and the universe became a clearer place to look through. Reionization is not just a historical label, it influences what kinds of galaxies could form, because ionized gas behaves differently from neutral gas. Astronomers piece together this era by combining evidence from distant galaxies' background beacons and the cosmic microwave background. It is one of the universe's great phase changes, like dawn arriving across all of space. Hydrogen absorption lines can map invisible gas between us and distant galaxies. Even when intergalactic gas is too thin to go on its own, it can still announce itself by stealing specific wavelengths from background light. When light from a distant source passes through hydrogen, it can lose intensity at characteristic wavelengths, leaving a series of absorption features. By measuring where those features appear, astronomers infer the gas along the line of sight, including its motion and its distribution over distance. This technique can be applied using bright quasars, and in some cases, using galaxies as background lamps as well. The pattern of absorption is not a single shadow. It is a layered set of imprints from many different clouds at many different distances that turns a one-dimensional sight line into a probe of the cosmic environment. It is a way of seeing what does not shine. The universe becomes readable not only by what it emits, but by what it blocks. That intergalactic gas record structure, like mist revealing a hidden landscape. The gas between galaxies tends to collect in the same large-scale patterns that galaxies do, because both respond to gravity. That means absorption features can trace filaments nodes and more tenuous regions, but are otherwise hard to map. With enough background sources, astronomers can do a kind of tomography, combining many sidelines to reconstruct a three-dimensional picture of intergalactic sea matter across a region of the sky. This approach is still developing, and it is one of the most exciting ways to connect galaxies to their feeding grounds. The gas is not just scenery, it is the reservoir that can supply future star formation, and it is the medium that carries metals outward from galaxies through winds. When you treat intergalactic gas as a record, you can ask new questions. Where does a galaxy's next fuel come from? Where do its outflows go? The answers live in the faint structured mist between the bright islands. Galaxy metallicity often rises over time as generations of stars live and die. Metallicity is the astronomer's word for elements heavier than helium, and it changes as a galaxy ages. Each cycle of star formation takes and gas builds heavier atoms through fusion, then returns some of that enriched material to the galaxy through winds and stellar brash deaths. Over long time scales, this tends to raise the abundance of elements like oxygen and carbon in the gas that will form the next stars. Astronomers measure metallicity in distant galaxies by studying emission lines from glowing gas in star-forming regions, then comparing line ratios that depend on temperature and composition. When they do this across cosmic time, a broad trend emerges. Younger eras tend to show lower metallicities, and later eras tend to show higher ones. The details matter because the rise is not uniform. It depends on how efficiently a galaxy turns gas into stars, how much gas flows in, and how much enriched gas flows out. Metallicity becomes a diary of a galaxy's past choices. Small galaxies can lose metals easily because their gravity is gentle. In a low-mass galaxy, escape is easier. That matters because the very events that create heavy elements also inject energy into the surrounding gas. When massive stars explode or drive strong winds, the hot enriched material can be launched outward as a galactic wind. If the galaxy's gravitational pull is weak enough, some of that metal-rich gas can leave for good drifting into the intergalactic medium. This helps explain why many dwarf galaxies remain chemically simple compared with larger galaxies that have had similar numbers of star-forming episodes. It is not only about how much they make, it is about how much they keep. Astronomers look for this effect by comparing metallicity to mass and by searching for signatures of outflowing gas in spectra. The picture that emerges is vivid. Small galaxies can be generous, donating newly forged elements to the space around them, even while they struggle to enrich themselves. Massive galaxies can hold on to enriched gas, building heavier elements more steadily. And a large galaxy can act like a deep bowl. Hot gas may be blown upward by energetic events, yet much of it stays bound and can later cool and fall back in. This process, sometimes described as a fountain, allows enriched material to be recycled rather than lost. Massive galaxies can also sustain extended halos of hot gas that trap outflows and mix them over time. The result can be a more consistent buildup of heavy elements, especially in regions where gas continues to form stars over long periods. Astronomers see hints of this steadiness in how metallicity correlates with galaxy mass, and in how metal-rich gas is distributed across galactic disks. This is not a simple story of keeping everything. Their galaxies still drive winds, and they still exchange matter with their surroundings. The difference is balance. Their deeper gravity makes it harder for valuable material to escape forever, and that helps them build complex chemistry over cosmic time. Some galaxies are red and dead, yet still grow. By swallowing smaller ones, a galaxy can stop making new stars and still keep gaining mass. In many large reddish systems, the remaining growth happens through dry mergers, which are mergers with little cold gas. Instead of triggering bright new star formation, the incoming smaller galaxies mostly add their existing stars. Over time, this can build up a wide, faint outer envelope, so the galaxy becomes larger without getting much bluer. Astronomers spot this kind of quiet growth by measuring how galaxy sizes change with cosmic time and by finding faint stellar shells or subtle gradients that suggests past accretion. It is a different style of evolution. The galaxy's central light can look settled and old, while the upskirts quietly thicken like rings in a tree. This also helps explain why some giant galaxies are so huge today. Their growth did not require constant star birth. It required patient gravity and many small arrivals. Galaxy cannibalism is slow, but he can dramatically reshape a galaxy's halo. When a large galaxy captures a smaller one, the process can take a very long time. The smaller system orbits, loses energy, and gradually dissolves under tidal forces. Stars are stripped first from the outskirts, then from deeper regions, until the original galaxy is spread into a faint looping halo of debris. These stellar halos are hard to see, but deep imaging reveals them as delicate arcs, shells, and streams around nearby galaxies. Each feature is a clue about the orbit of the swallowed companion and about when the encounter happened. Astronomers can even compare the chemistry of high-low stars, because a captor dwarf often carries a distinct chemical fingerprint. This is how a galaxy's outermost regions become a kind of scrapbook. The bright central galaxy is the main text, but the halo is the margin full of annotations. Cannibalism is not a single bite. It is a long reshaping meal that changes the galaxy's silhouette and its history. A galaxy's bulge can grow when stars are thrown into random orbits. Spiral galaxies often have a central bulge, a rounded concentration of stars that looks different from the flat disk. One way to build that bulge is to scramble. Stellar motion, close encounters, internal instabilities, and minor mergers can shake a disk, so that some stars are kicked out of orderly rotation. Instead of circling neatly in a plane, they begin moving in many directions, and the central region thickens into a bulge. This is more like stirring than stacking. It does not require new stars to appear. It requires existing stars to be rearranged by gravity. Astronomers study bulges by measuring how stars move and by examining how bulge properties relate to the rest of the galaxy. Some bulges look old and classical, as if built by violent early events. Others look more gradual, as if built by slow internal evolution. Either way, the bulge is a record of how stable the disk has been and how often it has been shaken. Stars in spiral galaxies can funnel gas inward, feeding central star formation. A bar is a long, bright structure of stars cutting through the center of a spiral galaxy. It is not just a visual flourish, it can act like a conveyor belt. The bar's gravity can torque the gas in the disk, nudging it inward over time. As gas drifts toward the center, it can pile up into dense rings or central reservoirs, and those reservoirs can ignite new star formation close to the core. This changes a galaxy's layout from the inside. The outer disk may form stars slowly, while the inner region flares with activity. Bars can also evolve, strengthen, weaken, and even dissolve depending on how mass is distributed and how the galaxy interacts with its surroundings. Astronomers spot the effects of bars by mapping gas flows and by comparing star formation patterns in barred and unbarred spirals. A bar is a quiet architect. It rearranges a galaxy's fuel without needing a collision from outside, and it can rewrite the central story over billions of years. Galactic rings can form after impact, like ripples in a cosmic pond. Sometimes a smaller galaxy plunges through the disk of a larger one, and the result can be a ring. The collision sends a wave outward through the disk's gas and stars compressing material as it travels. Where the wave compresses, gas star formation can light up in a circular pattern, creating a striking ring that expands over time. These rings are not permanent ornaments, they are moving consequences of an encounter. Astronomers can estimate the ring's age by its size and by the ages of the stars within it, and they can use simulations to reconstruct the likely path of the Reb intruder. The ring often reveals a past event that the galaxy's current appearance might otherwise hide. It is a beautiful example of cause and effect at galactic scale. One moment of impact can launch a long, graceful response. The galaxy keeps evolving, but the ring preserves the memory in a shape you can see. Polar ring galaxies show stars orbiting at odd angles, hinting at past mergers. In a polar ring galaxy, a ring of stars and gas orbits almost perpendicular to the main disk. It looks like one galaxy wearing another galaxy's belt. This strange geometry is strong evidence of a complicated past. A polar ring may form when a galaxy captures gas from a passing neighbor, or when a smaller galaxy is torn apart, and its material settles into an orbit that is tilted relative to the original disk. Because the ring is at such an unusual angle, it becomes a sensitive probe of the galaxy's gravitational shape. If the unseen mass distribution is slightly lopsided, the ring's orbit will respond. That makes these galaxies valuable laboratories for studying how mass is arranged beyond the visible stars. Astronomers observe polar rings in multiple wavelengths to track both young star formation in the ring and older stars in the host. The result is a single system that carries two orbital stories at once. It is a living diagram of how galaxies acquire material from outside themselves. Some galaxies have almost no spiral arms, just smooth light and old stars. Not every disk galaxy is rich with grand curling arms. Some appear smooth and featureless, with starlight that looks evenly spread and dominated by older stars. These galaxies can teach a quiet lesson about structure. Spiral arms are patterns that depend on how mass rotation and gas are arranged. If a galaxy has little cold gas, or if its disk is dynamically heated, so stars have more random motion, spiral structure can fade. Environment can matter. 2. A galaxy that has been stripped of gas in a crowded region may lose the ingredient that makes bright arm-tracing star formations stand out. Astronomers study these smooth disks by mapping their rotation and by measuring how the ages of their stars vary from center to edge. They can look like galaxies in retirement, still rotating, still shining, but no longer drawing dramatic patterns across their disks. The absence of arms is not emptiness. It is information about stability, fuel, and past interactions. Irregular galaxies can look messy, yet their chaos tells a precise history. An irregular galaxy can feel like a spill of starlight with no obvious symmetry, and no neat spiral design that messiness is often the point. Irregular shapes can come from tidal stresses, recent bursts of star formation, or a history of uneven gas inflow in small galaxies. Even modest events can leave strong marks because their gravity is weaker and their structure is easier to disturb. Astronomers decode irregulars by measuring where young stars are clustered, where gas is concentrated, and how different regions move relative to each other. Sometimes the galaxy's brightest regions are not at the center. Sometimes the gas disk is offset or twisted. These are clues that something happened even if it happened long ago. Irregular galaxies are also important because they resemble the kinds of systems that were more common in the early universe. Studying them nearby is like studying a living analog of youthful galactic behavior. Their chaos is a readable signature, not a failure of form. Tidal tailies are long starry streams pulled out by gravitational encounters. When galaxies pass close gravity, can grab their outer stars and gas like taffy. The result can be tidal tailies' enormous extensions that arc far beyond the main bodies. These tailies are not just decoration. They show that galaxies are not rigid objects. Their outer regions are loosely bound and easily reshaped. Tidal tails can also become highways for gas channeling material into new regions and sometimes triggering star formation along the tail itself. Astronomers use the shape and length of tails to infer the geometry of the encounter, including how close the galaxies passed and how their orientations were aligned. In some systems, you can see two tails pointing in different directions, each one tracing a different gravitational response. Over time, tailies can fall back, disperse, or remain as faint structures in a galaxy's outskirts. Either way, they are evidence that galaxies evolve through interaction and that gravity can sculpt with a surprisingly delicate hand. Those tailies can form new dwarf galaxies, born from torn-off debris. In some tidal tailies, clumps of gas and stars become dense enough to collapse into self-bound objects. These are often called tidal dwarf galaxies. Unlike many dwarfs that formed within their own dark matter, halos early on tidal dwarfs are built from recycled material, pulled out of larger galaxies that gives them a distinctive character. They can be relatively rich in heavy elements for their small size because the gas they are made from has already been enriched inside a bigger galaxy. Astronomers search for these newborn dwarfs by looking for bright knots in tidal tails and measuring their motions to see whether they are gravitationally bound, not just passing condensations. This is a remarkable kind of second-generation creation. A collision can tear galaxies apart and also create new structures in the same act, like sparks thrown from a grinding wheel. It reminds us that galactic evolution is not only about destruction, it can also be about recycling with new small galaxies emerging from the debris of larger ones. The Hubble Deep Field changed astronomy by revealing galaxies everywhere we looked. In the 1990s, astronomers pointed Hubble at a tiny patch of sky that seemed almost empty. It was a risky choice because telescope time is precious. After days of exposure, the image came back crowded with galaxies, far more than many people expected. The result did not just add pretty pictures, it changed intuition. It showed that even a dark-looking region is likely filled with distant systems, and it made the universe feel less like scattered islands and more like a vast populated ocean. It also gave researchers a new way to study galaxy evolution, because the same image contained nearby galaxies and extremely distant ones. Together, the deep field became a cultural turning point too. It was a reminder that the universe rewards patience and that looking longer can turn emptiness into abundance. The ultra-deep field pushed farther, showing even fainter and earlier galaxies. The ultra-deep field took the same basic idea and made it more extreme. By collecting light for much longer, it reached down to galaxies that are so dim they were previously invisible. This matters because faint often means far, and far often means early. The image became a kind of deeper archive, filled with small reddish smudges that hint at youth and distance. It also exposed a practical truth about discovery. Many secrets are not hidden by complexity. They are hidden by faintness. When you integrate for long enough, the universe slowly hands over photons that have been arriving all along. The ultra-deep field also gave astronomers a stronger sample for statistics. Instead of building cosmic history from a few bright oddities, they could include more ordinary galaxies from early times. The picture of the young universe became richer, messier, and more realistic. The James Webb Space Telescope sees early galaxies in infrared light. Webb was designed for a universe where the most ancient starlight has been shifted out of visible colors. Infrared is where that stretched light lands, and Webb's sensitivity there is extraordinary. That means it can spot galaxies that are both far away and intrinsically faint, including systems whose visible light would be swallowed by distance and dust. Webb also carries spectrographs that can read chemical fingerprints from very early times, turning tiny patches of light into physical information about gas stars and motion. This changes what early galaxies feel like. They stop being anonymous dots and start becoming places with measurable properties and surprising variety. Some appear compact and intense, others look extended and structured earlier than expected. Each observation feeds back into our models of how galaxies assembled. Webb does not just extend our reach, it changes the questions we dare to ask about the first major chapters of galaxy formation. Webb can detect ancient starlight at dust and distance once hid. Dust is a master of disguise, invisible light, and distance weakens everything. Infrared offers a way around both problems. Longer wavelengths pass through dusty regions more easily, and they match the red-shifted glow of old faraway stars. With Webb, astronomers can identify galaxies that were previously undercoated because they looked unimpressive or nearly absent in optical surveys. This is important for cosmic bookkeeping. If you miss dusty star-forming galaxies, you misjudge how quickly the universe built its stellar mass. Webb can also separate different components inside a galaxy, because dust heated by star formation has a different infrared signature than starlight from older populations. That separation helps clarify what is power in the light we receive. In a way, infrared observing is an honesty test. It checks whether a galaxy is truly quiet or whether it is active behind curtains that older instruments could not see through. Some early galaxies appear larger than expected, sparking debates about rapid growth. When observations hint that surprisingly substantial galaxies existed very early, it forces a careful pause. Are we seeing galaxies that truly built up mass faster than our models predict? Are we seeing systems that look larger because of how their light is distributed? Are lenses magnifying them in subtle ways? These questions matter because galaxy growth is tightly linked to the behavior of dark matter gas, inflow, and star formation efficiency. A single surprising population can reveal missing physics, or it can reveal how difficult the measurements are at the faintest limits. Astronomers respond by cross-checking sizes, redshifts, and masses with multiple methods, and by looking for consistent patterns across different fields of sky. The debate itself is part of the excitement. The early universe is a harsh proving ground for theory. If large galaxies really did appear quickly, we learned something profound about how efficiently nature can assemble structure in a short cosmic window. Astronomers test their surprises by improving distances, lenses, and galaxy modeling. When a result looks too strange, the first job is to challenge every step that produced it. Distances depend on redshift estimates and on how spectra are interpreted. Lensing can boost brightness and stretch shapes, so models must account for foreground mass even when it is faint. Stellar masses depend on assumptions about how stars form, how bright they are at different ages, and how much dust is dimming them. Astronomers tighten these uncertainties by getting deeper spectra, by comparing independent instruments, and by running simulations that forward model what a Bay telescope should see. They also revisit calibration details because small biases can become big at the edge of detectability. This process is not a retreat, it is the engine of progress. Either the surprising galaxies become less surprising, or the case strengthens until theory must adapt. In both outcomes, the universe wins because our picture becomes sharper and more trustworthy. Better instruments can turn a dot into a measured galaxy with structure. A faint galaxy can begin as a single unresolved point with higher resolution and sensitivity. That point can split into a shape, and the shape can reveal a story. You might see a stretched arc that hints at lensing. You might see a compact core surrounded by diffuse light, suggesting different stellar populations. You might see multiple clumps implying a turbulent stage of assembly. Spectroscopy can add a second dimension, showing whether gas is rotating, flowing outward, or split into separate components. This is one of the most satisfying arcs in astronomy. The object does not change our ability to interrogate. It does. Each technological leap converts mystery into measurement, and measurement into new mystery. It also teaches patience with the unknown. Many galaxies that were once classified broadly or dismissed as featureless become nuanced when the data improves. A dart is often just a galaxy waiting for better questions and better tools. Long the exposures collect faint photons, like filling a cup one drop at a time, deep observing as an active accumulation. For very distant galaxies, photons arrive rarely, and they arrive mixed with noise from the detector and background light. A longer exposure increases the total signal, while noise grows more slowly, so the galaxy gradually emerges. Astronomers often take many shorter images and stack them, which helps remove cosmic ray hits and other artifacts. The final picture can feel sudden, but it is built from patience and careful processing. Long exposures also demand stability. Pointing must be precise and calibration must be consistent, or the faint signal smears away. The reward is access to populations that are otherwise absent from our view, including low surface brightness galaxies and the earliest systems at the edge of VT detectability. This is why deep fields matter. They show what the universe looks like when you stop glancing and start listening. The photons were always coming. We simply needed to stay long enough to meet them. Space telescopes avoid Earth's atmospheric blur, making faint galaxies easier to separate. Earth's atmosphere is a wonderful shield for life, but it is a restless lens for astronomy. Turbulence makes starlight wobble, and that wobble spreads a faint object's light over more pixels, lowering contrast from orbit. A telescope avoids that blur and can deliver sharper images with stable backgrounds. Sharpness is not just about beauty. It helps distinguish a distant galaxy from a nearby star, and it helps separate small galaxies that would otherwise blend together. It also allows more accurate measurements of size and shape, which become crucial when you are comparing galaxy structure across cosmic time. Space telescopes can also observe wavelengths that the atmosphere blocks or absorbs, including much of the ultraviolet and parts of the infrared that access broadens the story you can tell about galaxies, from young hot stars to dust warmed by star formation above the air. The sky becomes quieter and faint galaxies become easier to hear. Adaptive optics on Earth can also sharpen galaxy views by correcting air turbulence. Adaptive optics is a clever answer to a stubborn problem. If the atmosphere is distorting incoming light, you can measure the distortion and correct it in real time. Systems do this by observing a reference source, sometimes an artificial laser guide star, then flexing a deformable mirror hundreds of times each second. The result can approach the clarity of spaced imaging, especially in infrared wavelengths for distant galaxies. This can reveal fine structure from the ground, including compact cores, clumps, and close pairs that might otherwise blur together. It also enables detailed spectroscopy at high spatial resolution, so astronomers can map motions across a galaxy rather than averaging everything into C. Day one's signal adaptive optics does not replace space telescopes, it complements them, because ground-based observatories can be enormous and can host instruments that are hard to fly. Together, they create a powerful partnership. Space provides stability and darkness. The ground provides size and flexibility. With the atmosphere increasingly tamed by technology, galaxy surveys map millions of galaxies, building a three-dimensional universe. A sky full of points can become a real map when you at distance. Large surveys do this by measuring galaxy positions and then estimating how far away each one is, often using redshift. The result is not a flat star chart. It is a volume, a slice of the cosmos with depth. When you fly through these maps in a visualization, you see filaments. knots, and emptier regions that would be invisible in a simple photograph. These surveys also reveal how different kinds of galaxies occupy different neighborhoods. Bright, massive systems prefer dense regions, smaller ones are more widely scattered. Every new SIR, they expands the census and sharpens the pattern, and it turns abstract ideas about structure into something you can almost navigate. It is one of the astronomy's most ambitious acts. We take faint, distant smudges, and we place them into a coherent architecture that spans billions of light years. Those maps let us measure how structure grew and how dark energy behaves. Once you have a three-dimensional map, you can compare it to what the universe should look like under different cosmic rules. Gravity tries to pull matters together, so structure should grow over time. Cosmic expansion works against that, and dark energy appears to make expansion speed up. The balance between these effects leaves signatures in how clumpy the galaxy distribution is at different distances, which correspond to different eras. By measuring clustering strength across time, astronomers test whether the universe grew structure at the rate predicted by our best models. Small differences matter because they could hint at new physics. These maps are also cross-checked with other probes, so the story is not carried by one method alone. In the end, the galaxy map becomes more than a catalog. It becomes a measurement of the universe's behavior, telling us whether gravity and expansion have been playing by the expected rules or whether something subtle is still missing. Baryon and acoustic ripples leave a subtle spacing pattern in galaxy distributions. In the early universe, ordinary matter and light were coupled in a hot plasma. Sound waves could travel through that mixture, pushing matter outward in expanding shells. When the universe called enough for light to decouple, those waves froze into a faint preference for a particular scale in the distribution of matter. Billions of years later, that preference still lingers as a slight bump in how often galaxies are separated by a certain distance. It is not obvious by eye, and it takes huge samples to detect. Yet once measured, it is incredibly useful because it comes from early physics that is well understood. This is one of the most delightful ideas in cosmology. The sound wave from the infant universe left a quiet imprint that modern galaxy maps can still find. It is like hearing an ancient echo, not with your ears, but with statistics written across the sky. That spacing acts like a cosmic ruler, helping measure the universe's expansion. Because that preferred separation scale is known, it can be used as a standard ruler. If the ruler appears stretched or squashed at different distances, it tells you how the universe has expanded between then and now. Astronomers measure this scale in galaxy surveys, then compare it across redshift to reconstruct the expansion history. This helps pin down key parameters that describe our cosmos, including how quickly expansion is changing. The method is powerful because it is geometric. It does not rely on the brightness of individual objects in the same way some distance methods do. Instead, it relies on a pattern across many galaxies, which makes it more robust to the quirks of any single system. It also connects a late-time measurement to early universe physics, tying together two mends of cosmic history. A ruler made from ancient sound becomes a tool for modern cosmology, and it lets us measure the universe at a scale that feels almost impossible. Galaxy clustering shows where matter gathered, even when much of it is invisible. Galaxies do not sit alone. They cluster because they formed in regions where matter was slightly denser to begin with, and gravity amplified those differences. When astronomers measure clustering, they are indirectly measuring the underlying matter distribution, including the dark matter that does not emit light. The shape of clustering changes with scale. Small scales tell you about groups and clusters. Larger scales tell you about the broader cosmic web. Clustering also depends on galaxy type. Some galaxies are more biased traces, meaning they live preferentially in dense environments, so their clustering is stronger. By comparing different populations, astronomers learn how galaxies occupy dark matter halos and how that relationship changes over time. This is not just a census of where galaxies are. It is a way to infer where masses and how it assembled. The luminous universe becomes a tracer die in a much larger, mostly invisible fluid and the patterns it reveals are rich with information. Weak lensing subtly stretches many galaxies, revealing hidden mass across the sky. Most gravitational lensing is not dramatic rings and arcs. Much of it is weak lensing, a tiny systematic distortion imprinted on the shapes of distant galaxies by the cumulative mass between them and us. Any one galaxy shape is noisy because galaxies are naturally varied. The trick is to measure millions of them and look for a shared directional stretch. That shared signal maps the distribution of mass on large scales, including dark matter. It is like feeling a faint current in a river by watching how many leaves drift. Weak lensing is demanding because it requires exquisite image quality and careful correction for instrumental effects. When done well, it becomes one of the cleanest ways to weigh the universe. It does not ask mass to glow, it asks mass to bend light. The result is a mass map that can be compared with galaxy maps, and the agreement or mismatch teaches us how visible matter and dark matter trace one another through cosmic time. Strong lensing can measure a cluster's mass with remarkable precision. When the alignment is right and the foreground mass is enormous, lensing becomes strong. Background galaxies are stretched into arcs and sometimes multiplied into several separate images. The exact positions and shapes of those images depend sensitively on the gravitational field of the lens, so modeling them allows astronomers to infer the cluster's mass distribution. This is especially striking because clusters contain large amounts of dark matter, far more than what is visible in their galaxies alone. Strong lensing can also reveal substructure, smaller clumps of mass within the cluster, because those clumps tweak the images in measurable ways. In some cases, lensing magnifies a background galaxy so much that it becomes accessible for detailed study. So one phenomenon provides two gifts at once for clusters. Strong lensing is a practical scale. It turns cosmic geometry into a weighing tool, and it lets us test how matter is arranged in the largest gravitationally bound systems in the universe. Some galaxies are aligned by their environment, shaped by the pole of neighbors. Galaxies are not always oriented at random in dense regions and along filaments. Their spins and shapes can show faint alignments that reflect the tidal forces that helped form them. As matter flows along the cosmic web, it can talk of forming galaxy, nudging its rotation axis into a preferred direction. Later interactions can reinforce or disrupt that tendency, depending on how crowded the neighborhood becomes. Detecting alignments takes careful statistics because the effect is subtle and chance can mimic a pattern. Yet it matters for two reasons. First, it is another clue that galaxies and the cosmic web grow together. Second, it can affect weak lensing studies because lensing also produces alignments, and the two signals must be disentangled. So these quiet orientations become both a science target and a calibration challenge. The environment does not only determine what galaxies live near, it can also leave a fingerprint on how they are angled in space, as if the web itself has a preferred grain. Cluster galaxies can be stripped of gas as they plow through hot intracluster plasma. Inside a galaxy, cluster space is filled with very hot, thin gas. When a galaxy moves through that medium at high speed, it experiences a pressure like wind. This ram pressure can push the galaxy's own gas out of its disk, especially the more loosely bound gas in the outskirts. In some observed cases, galaxies show long tails of gas trailing behind them like banners streaming in a storm. This stripping changes a galaxy's future because gas is the ingredient for star formation. Removing it is like taking away the pantry. The process can be sudden compared with other galaxy changes because one fast pass through a dense region can do serious work. Astronomers study stripped galaxies in multiple wavelengths, since the displaced gas can glow in different ways, depending on temperature and density. The cluster environment becomes an active force, not just a setting. A galaxy entering a cluster is not only joining a crowd, it is entering a place where the medium between galaxies can reshape what a galaxy is able to become. That stripping can shut down star formation, turning blue galaxies red over time. When a galaxy loses its cold gas, the bright blue phase does not end instantly. Existing massive stars still shine, but they live short lives. As they fade, the galaxy's light becomes dominated by longer-lived redder stars, and the whole system gradually shifts in color. In clusters, this can create a population of galaxies that look older and more quiescent than similar galaxies in less dense environments. The transition can also happen through starvation, where a galaxy keeps its disk gas for a while, but stops, receiving fresh supplies, so the fuel runs down. The slowly stripping is more abrupt, and it can leave telltale signs like asymmetric gas disks and one-sided tailies. Astronomers connect these clues to a galaxy's position and speed within the cluster to reconstruct the sequence. The color change becomes a visible outcome of an invisible process, and it shows how environment can control galaxy evolution without a dramatic collision. A cluster does not have to smash a galaxy to change it. Sometimes it simply blows the fuel away. Some distant galaxies host enormous halos of glowing hydrogen called Lyman alpha blobs. These objects can look like vast hazy clouds wrapped around young galaxies, sometimes stretching far beyond the visible starlight. The glow comes from hydrogen releasing a specific kind of ultraviolet light which arrives to us, shifted into longer wavelengths by cosmic expansion. What makes them so fascinating is their scale. The luminous gas can extend across regions large enough to swallow a whole galaxy group. In images, the bright cores may look like small knots, while the surrounding halo spreads out like a low luminous fog. Astronomers study their shapes to learn how gas is arranged around forming galaxies, and how that gas connects to the larger cosmic web. Some blobs appear in crowded regions where many galaxies are assembling at once, which hints that these halos may be signposts of energetic growth bear like neon outlines of otherwise invisible surroundings. Those blobs may be powered by star formation cooling gas or active black holes. The mystery of alignment alpha blob is not only that it glows, it is why it glows so strongly over such a large volume. One possibility is intense star formation. Hot young stars can flood their surroundings with energetic photons that excite hydrogen. Another possibility is a central black hole that is actively feeding. An active nucleus can pour out radiation that lights the gas up from within. A third idea is cooling radiation, where gas falling into a halo sheds energy as it cools, and some of that energy emerges as hydrogen emission. The challenge is that these mechanisms can overlap and hydrogen light can scatter, which makes the glow look more spread out than the power source really is. Astronomers tease them apart using multi-wavelength observations, line shapes, and the presence of other emission features. In the best cases, the blob becomes a detective story with several suspects, and the evidence is written in faint, extended light. The brightest galaxies and clusters often sit near the gravitational center. In many clusters, one galaxy stands out as the giant in the crowd. It tends to sit close to the cluster's deepest gravitational well, where the overall mass is most concentrated. This central position is not a coincidence. Over long times, galaxies lose orbital energy through interactions with the cluster environment, and massive galaxies are more likely to sink inward. As companions spiral closer, they can be accreted, adding stars to the central galaxy's outer regions. The result is often an enormous system with a broad, faint envelope that blends into the cluster's background glow. These central giants are useful because they trace the cluster's structure, their location, and help identify the cluster center, and their properties reflect a long history of growth in a dense environment. When you look at one, you are seeing the outcome of many slow gravitational negotiations, where the center gradually collected what the cluster offered. The intracluster light is made of stray stars, orphaned by past collisions between the galaxies. In a cluster, there can be a faint glow that does not belong to any single galaxy. It comes from stars that were stripped away during interactions, close passes, and mergers. Once freed, those stars orbit the cluster itself, not their original homes. This makes intracluster light both delicate and revealing. It is difficult to observe because it is spread thinly across a large area, and it can be overwhelmed by brighter sources. Yet when it is detected, it acts like a fossil record. The amount of intracluster light and the way it is distributed hints at how violently the cluster has been assembled. It can show where the galaxies have been shredded frequently and whether the cluster has had recent mergers with other clusters or groups. Astronomers also study the colors of this glow to learn what kind of stars were stripped. It is a haunting idea. A cluster can contain a population of wandering stars living in the space between galaxies. Some galaxies are ultra-diffuse, spread out like ghostly smears of starlight. An ultra-diffuse galaxy can be large in size yet so faint that it almost disappears into the background. Instead of a bright core and crisp features, its light is spread thinly like a watercolor washed across the sky. This makes these galaxies easy to miss, and it makes their existence feel surprising. How can something so extended avoid collapsing into a denser, brighter form? One clue is that they often live in challenging environments, including galaxy clusters, where interactions and heating can reshape gas and slow the formation of new stars. Another clue is that their stars are spread out, which suggests a different history of assembly or internal dynamics than typical compact dwarfs. Astronomers find them using deep, careful imaging that can detect very low surface brightness features. Once found there, raise a wonderful question. Are they failed giants that never built many stars, or puffed up dwarfs shaped by their surroundings? Their faintness is not emptiness, it is a signature. Ultra-diffuse galaxies can still contain lots of dark matter despite their faintness. Some ultra-diffuse galaxies look like they should be fragile, yet they can survive in environments that would tear apart a truly lightweight system. That durability hints that something unseen is helping hold them together. Astronomers test this by measuring the motions of stars or by counting and tracking globular clusters that orbit within the galaxy's gravitational reach. If those tracers move faster than the visible stars alone can explain, it suggests a substantial dark matter halo. That is a striking contrast. The galaxy's light is thin, but its gravity can be strong. This combination challenges simple assumptions about how starlight relates to Mars. It also opens several possibilities. Some ultra-diffuse galaxies may be extreme cases of normal galaxy formation, where star formation was inefficient. Others may have had their gas removed early, leaving behind a faint stellar population inside a massive halo. Each case helps refine our models because it forces us to separate what we see from what truly shapes the system. Some galaxies are almost pure gas with surprisingly few stars. There are galaxies where the starlight is minimal, yet the gas reservoir is enormous. In these systems, the usual story of gas rapidly turning into stars seems to have stalled. The gas can be diffuse, spread out, and stable against collapse, which makes it harder to form dense star-forming clouds. Low metallicity can also play a role because fewer heavy elements can make cooling less efficient. And cooling is part of the path towards star formation. Some of these galaxies are discovered through radio surveys that detect neutral hydrogen long before they are recognized in visible light. They are fascinating because they feel like galaxies waiting to begin, or galaxies that began and then hesitated. They also serve as laboratories for understanding what star formation requires and what can prevent it even when raw material is present. If you want to know why galaxies light up, it helps to study the ones that stay mostly dark. Others are star-rich, but Gusper showing their fuel was exhausted or removed. A gas-poor galaxy can look luminous and settled, yet it carries a quiet warning, but the supply line is gone. Some galaxies use up their gas over long periods, turning much of it into stars until the remaining reservoir is too small to sustain further star formation. Others lose gas through environmental effects, such as stripping in clusters, or through energetic internal events that heat or expel the gas. The result is a system where the stellar population dominates, and the usual signs of ongoing star birth are faint or absent. Astronomers identify gas poverty by looking for weak radio signals from hydrogen by measuring low molecular gas content and by examining spectra that lack strong emission from star-forming regions. These galaxies are important because they show that galaxy evolution has off-ramps. A galaxy can transition from building to aging, not because stars stop shining, but because the conditions for making new ones have been shut down. The stars remain as a record of past abundance, while the missing gas hints at what changed. Galaxy rotation curves helped reveal dark matter, one of astronomy's biggest shocks. The shock was not only that galaxies rotate, it was how their rotation behaves with distance from the center. Astronomers expected outer regions to slow down because most visible mass is concentrated toward the middle. Instead, measurements showed that the outer parts often keep moving fast. This was established through careful work on the motions of stars and gas, including observations of hydrogen in radio wavelengths that extend well beyond the bright greater stellar disk. The implication was unavoidable. There must be additional mass spread widely around the galaxy, far beyond what the light suggests. This idea reshaped modern cosmology because it meant the universe contains a dominant component that does not glow. It also changed the way astronomers think about galaxies. A galaxy is not only its stars, it is a luminous core embedded in a much larger gravitational structure. The rotation curve became a turning key that unlocked a hidden majority. The Tully-Fisher relation links a spiral's rotation to its brightness and mass. Spiral galaxies have a remarkable habit: the faster they rotate, the more luminous they tend to be. This connection is not perfect, but it is strong enough to be useful. Astronomers can measure a galaxy's rotation speed from the width of spectral lines, then use the relation to estimate how intrinsically bright the galaxy should be. Compare that intrinsic brightness with how bright it looks from Earth, and you can infer its distance. That makes the relation a practical run on the cosmic distance ladder, especially for mapping the nearby universe beyond our immediate neighborhood. It also hints a deep order in galaxy formation. Rotation speed reflects the gravitational pull of the galaxy's mass, including its dark matter. Halo brightness reflects the amount of starlight. The fact that these two track each other suggests that the building of stars and the shaping of halos are connected, even if the details are still being refined. It is a bridge between what we can measure easily and what we want to know. Elliptical galaxies follow a different rule where random motions support the stars. In a spiral galaxy, the disk is held up by rotation, with stars moving in an organized swirl. In an elliptical galaxy, a support comes from something that looks more like a busy crowd. Stars move on many different paths, crossing in every direction, and that random motion provides the pressure that balances gravity. Astronomers reveal this by taking spectra across the galaxy and measuring how broadened the stellar absorption lines are. Broader lines mean a wider range of speeds. This difference changes how ellipticals age and how they respond to encounters. Without a thin, orderly disk, there is less obvious structure to disturb. Yet ellipticals can still carry subtle clues like shells and gradients, but hint at their assembly history. When you understand the role of random motion and elliptical stops, being a smooth blob, it becomes a dynamic system with countless stellar journeys woven into one steady glow. The fundamental plane ties an elliptical-sized brightness and internal speeds together. Elliptical galaxies may look simple, but they obey a surprisingly tight relationship. If you know how large an elliptical is, how bright its light is spread across that size, and how fast its stars are moving inside. Those three quantities line up on what astronomers call the fundamental plane. This is not a literal plane you can see. It is a mathematical pattern that suggests ellipticals are governed by shed physics, and that their structures are not arbitrary. The relation lightly reflects how gravity, mass distribution, and stellar populations work together. After a galaxy settles, astronomers use it as both a diagnostic and a tool. When a galaxy falls off the plane, it may have had an unusual history or unusual stellar content. When a population sits neatly on it, it tells you the group has reached a kind of equilibrium. It is right finding a hidden raw book beneath a smooth appearance, and realizing that the calm light is backed by consistent internal order. Some galaxies contain globular clusters that are older than most stars in their disks. Globular clusters are dense ancient gatherings of stars that orbit a galaxy like a swarm of tiny satellites. Many formed very early when the universe had fewer heavy elements and galaxies were still assembling their main structures. That means a galaxy can carry these clusters as relics from its earliest phases, even if its disk kept forming stars much later. When astronomers study globular clusters, they often find stellar populations that are remarkably uniform in age, and they can measure their chemical composition to infer how early they formed. These clusters are also hardy. Their tight gravity holds them together across cosmic time, surviving mergers and upheaval that can reshape a galaxy's disk. In a sense, they are fossils that move. They travel through a galaxy's halo, preserving a memory of conditions that no longer exist. In the same way, when you spot a globular cluster system, you are seeing a galaxy's deep past still intact and still orbiting. The number of globular clusters can hint at a galaxy's dark matter halo. Counting globular clusters is not just a census of star clusters. It can also be a clue to a galaxy's total mass budget. Across many galaxies, astronomers have found that richer globular cluster systems tend to be associated with more massive halos, including the unseen mass that dominates the outskirts. The idea is that building or retaining many globular clusters is easier in a depot gravitational well, especially early on when conditions were turbulent and gas was being gathered. This correlation is useful because globular clusters can be easier to identify than the faint outer halo of stars, and they can be traced to large distances from the galaxy's center. Observers use deep images to find these compact ancient points of light, then confirm them by their colors and motions. The relationship is not perfect, and it can vary with environment and history. Still, it offers a clever shortcut. Tiny clusters can act like signposts for a much larger invisible structure, giving you a way to estimate a galaxy's hidden heft from the company it keeps. Some galaxies have counter-rotating disks, suggesting a dramatic past acquisition of gas. In a typical disk galaxy, most stars and gas orbit in the same direction. Counter-rotation is the shock of finding a substantial component orbiting the opposite way, like two rivers flowing through each other. This configuration is hard to create internally. It usually points to outside material arriving later, such as gas captured from a neighbor or recreated from the surrounding environment with a different angular Dal-Par momentum. Over time, that acquired gas can form new stars that inherit its opposite spin, building a secondary disk inside the first. Astronomers detect counter-rotation by measuring Doppler shifts across the galaxy, then seeing the telltale reversal in velocity. The pattern can appear in gas alone or in stars as well, and each case hints at a different story of timing and mixing. Counter-rotating systems are exciting because they make history visible in motion. The galaxy's present-day rotation becomes a record of past encounters, and it reminds us that galaxies can be rebuilt from the outside in, without looking obviously disturbed in a simple image. Galaxy hearts can host dense star clusters, sometimes rivaling a black hole's influence. At the centers of some galaxies, there is a compact bright knot, but is not a black hole and not an active nucleus. It is a nuclear star cluster, packed with stars in a very small region. These clusters can contain multiple generations of stars, which suggests they grew over time through repeated inflow of gas and through the migration of smaller clusters inward. Their gravity can dominate the central region's dynamics, shaping how stars move and how gas settles. In some galaxies, a nuclear star cluster and a central black hole may even coexist, and their relative importance can change with galaxy mass and history. Astronomers study these clusters by resolving the central light and by measuring stellar motions to estimate the mass concentrated there. The result is a different kind of galactic core story. Not every center is ruled by a single dark object. Some are ruled by an intense crowd of stars, bright enough to stand out and massive enough to reshape the inner city of the galaxy. Many galaxies likely formed inside out, with older stars concentrated toward the center. A common growth pattern in disk galaxies is that the inner regions build up earlier, and the outer disk develops later as fresh gas settles at larger radii. This creates age gradients. The central parts tend to host older, more metal-rich stars, while the outskirts are often younger and more actively forming stars, at least for galaxies that still have fuel. Astronomers test inside-out growth by measuring stellar ages and compositions across a galaxy's radius using spectra and multicolor imaging separate populations. They also look for how star formation has shifted over time from centrally concentrated bursts to more extended disk activity. Inside-out formation helps explain why many galaxies have dense inner regions and more delicate outer structures. It also connects to angular momentum. Gas with higher angular momentum tends to settle farther out, so the later arriving material naturally extends the disk. When you picture inside-out growth, you are picturing a galaxy that is not built all at once. It is built in stages, with the center maturing first and the edges filling in later, like a city that expands outward from an old downtown. The universe's first galaxies help set the stage for every galaxy today. The earliest galaxies did more than shine. They changed their surrounding. Their stars produced intense radiation that altered the state of intergalactic hydrogen. Their winds and explosions pushed material outward, spreading the first heavy elements into the space between galaxies. Those elements later made cooling more efficient, helped dust form, and opened new pathways for building complex structures. Early galaxies also shaped the cosmic environment through gravity, gathering matter into the first nodes of the cosmic web and influencing where later galaxies would deep grow. Even their black holes may have seeded later generations of active nuclei, affecting how gas behaved in young halos. When astronomers chase the first galaxies, they are looking for beginnings that echo forward. Later galaxies inherit more than mass. They inherit conditions. They inherit enriched gas, a changed radiation background, and a web of structure already partly built. In that sense, the first galaxies are not just the earliest chapters. They are the opening scene that determines the lighting and the mood of everything that follows. Studying distant galaxies is how we learn what our own galaxy once was. We cannot take the Milky Way and rewind it like a film. We live inside it, and we see it only in its current state. Distant galaxies solve that problem by offering earlier versions of the same general processes. By comparing galaxies across cosmic time, astronomers can infer how disks assemble, how bulges grow, and how star formation rises and falls. Then ask which pathway best matches what we observe at home. Distant systems also show us what the Milky Way did not become. Some galaxies quenched early, some grew into giant ellipticals, some remain small and irregular. Those contrasts help narrow down the Milky Way's likely history. There is also a practical benefit. External galaxies let us measure structure directly, including bars, rings, and interactions in ways that are hard to see from inside a disk. Each faraway galaxy is a proxy experiment. It is a way to explore possibilities for our own past, using the universe's natural variety as a dataset. The story of distant galaxies is also indirectly a story of where we came from. Every new deep survey adds galaxies to our map and questions to our minds. Astronomy advances in a rhythm. A new survey pushes deeper or wider, and suddenly the universe looks more crowded, more structured, and more surprising. A deeper view finds fainter galaxies and rarer types. A wider view reveals how environments change the story from dense clusters to empty voids. Each increase in sample size strengthens what we think we know, and it also exposes the outliers that force new ideas. Sometimes the questions are about physics, like how efficiently gas turned into stars early on. Sometimes they are about measurement, like whether a distance estimate is being fooled by dust or lensing. Either way, the map grows, and the edge of the map becomes the most exciting place to stand. Deep surveys also create shared reference fields that scientists return to for years, layering new wavelengths and new techniques onto the same sky. The result is a living archive where the universe keeps offering more detail and where each answer is an invitation to ask a sharper question next. As we come to the end of our journey, the universe feels a little wider than it did before. We drifted past distant galaxies that shine from ancient time, and we watched light itself carry their stories across vast space. We lingered on crowded clusters and delicate streams of stars on hidden gas clouds and dusty regions where new suns are born out of sight. We followed the quiet logic of gravity as it bends light into arcs and rings, and we listened for the deep patterns that surveys uncover where galaxies gather along a prayer cosmic web like pearls on invisible threads. And in all of it, there was that steady feeling of perspective. Each faraway glow is not just a place, it is a moment preserved, a message arriving after an unimaginably long trip. Some galaxies grow through calm accumulation, some are reshaped by encounters. Some blaze with fierce activity at their cores, some fade into a slower, older light. Together, they tell one long story of change spread across the sky. If you enjoyed this voyage, you can support the channel with a subscription, or acquired comment before you drift off. It helps more curious minds find these episodes, and it keeps our nights of science and wonder going. Now you do not need to hold on to any of it, that the ideas settle like starlight, sinking into the horizon, that your jaw unclench, that your shoulders soften, and that your breathing find an easy rhythm. If you are still awake and you would like one more journey, there will be another video waiting on the screen, ready to carry you onward. Otherwise, simply rest here, the calm after the cosmos. Sleep well and good night.